Good afternoon. I'm Kalichuran, Chairperson of the KZN Centre of the South African Institute of Electrical Engineers. A warm welcome to our presenter, Dr. Muhhamad Daghrah, officials and members of the South African Institute of Electrical Engineers, and all other attendees. I hope you are all exercising caution, taking care, and keeping safe during the pandemic. Attendees, please ensure that the volume of your device is turned up and that you have stable internet connection for smooth streaming and audio. You can ask questions via the questions panel, which is located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. Questions will be answered at the end of the presentation. You will not be able to chat with each other. However, you are encouraged to ask questions. A recording of this presentation will be made available on the SAIEE YouTube channel SAIEE TV. The recording will also be made available on the SAIEE website under the Events drop-down menu in the section Past Events and Webinars. This page is updated regularly, so check as often as possible for new uploads. Do subscribe to our YouTube channel for more uploads. A certificate of attendance will be issued a few weeks after this webinar, once we have received the CPD validation number for this webinar from the Engineering Council of South Africa. Our presenter is Dr. Muhhamad Daghrah. Dr. Muhammad was awarded his PhD in Electrical and Electronic Engineering from the University of Manchester. His research was on transformer thermal modeling. He holds a BSc in Electrical Engineering from the Birzeit University in Palestine and an MSc in Electrical Power Systems Engineering from the University of Manchester. In 2018, Muhammad joined MIDEL's technical team as an applications engineer with responsibilities involving technical support for customers, leading research in understanding transformer thermal behavior with alternate liquids, attending exhibitions, and speaking at technical conferences worldwide. The topic this afternoon or today is Ester Fluids for Power Transformers. The presentation will cover all aspects of ester fluids, like overview of esters, fire and environmental impact, retrofit solutions, maintenance of the fluid, its benefits to asset managers, references in the market, testing and analysis of the fluid, case studies, and cost comparisons. With that, it's over to you, Dr. Muhammad.
Thank you very much, Jay, and I welcome everyone for this webinar. Thank you very much again for having me today. And thanks for introducing me, so I don't need to go through this slide. I'm happy to be presenting to the SAIEE today regarding the topics which you introduced, esters for power transformers. For today's presentation, the content as follows. I thought for 1 hour is good to go very brief on the key features of esters and why people use them, mainly because of their less flammability and also reduced impact on the environment. The second, we go a little bit more technical on how we design transformers for esters. In this second section, I lightly touch on the electrical aspect and also the thermal aspects. And then the third item here for utilities is retrofilling. Sometimes you have an existing transformer and the benefit of an end user is to, instead of buying a new transformer, is to retrofill with an ester to gain the key benefits of these fluids. And so we talk about the process, how we identify a transformer as a good candidate for retrofilling. And of course, when a utility start adopting or using another liquid, We need to learn how we maintain our fluids and assess our transformers, if they are in good shape or not. And of course, esters are different from mineral oil. They do give some benefits to asset managers. We review these, some case studies and cost comparison. And at the end of this, please forward your questions as indicated earlier by Jay. So let's go now for the first section of this presentation about the key features of esters. Now, esters in the market, which are used in transformers, either power transformers or distribution size transformers, can be synthetic esters or natural esters. A synthetic ester basically is a man-made ester in a factory by using carefully selected alcohol and acids. We mix them together to make a robust product, a dielectric fluid used in the transformer application. Another branch of esters are the natural esters, which are extracted from vegetable oils. These could be soybean oils or rapeseed oils. Of course, the natural ester is affected by its base oil, so disregarding its oxidation stability, pour point, and other parameters. And one item here to emphasize as the key difference between a synthetic ester and a natural ester is the oxidation stability. Natural esters should only be used in sealed transformers where there's no exposure to atmospheric air and oxygen. Now, this table, I'll spend a little bit more time here because it really shows the key differences between mineral oil and esters. In this table, you see 4 columns. The first one is mineral oil. This is a typical mineral oil values. This next to it is MIDEL EN 1215, which is a soybean-based natural ester. Right hand to it is MIDEL EN 1204, which is a rapeseed or canola-based natural ester. And finally, you have the synthetic ester MIDEL 7131. So you have in this table a mineral oil, a natural ester, and a synthetic ester. On the first column, you see certain parameters that are of interest to compare between mineral oil and esters. The first one, of course, is the fire safety. Esters are mainly used in transformers because they offer elevated fire safety. And how we classify that is using the fire point and the net calorific value. So let's first talk about mineral oil. Mineral oil is known as an O1 class liquid. And O meaning its fire point is lower than 300 degrees. So you see in the table a typical fire point value for mineral oil is 170 degrees. And also mineral oil has a lot of energy in it. It has high net calorific value, more than 46 megajoule per kilogram, meaning when it burns, it will release a lot of energy. Now, esters have different story. They are classified as K-class fluids. The reason being they have fire point higher than 300 degrees. MIDEL EN are the natural esters. They have typically fire point higher than 350 degrees, while MIDEL 7131 is the synthetic ester, has a fire point typically higher than 300 degrees. So this is the first one, is the fire point, and this really contributes how you space your transformers from one another in a substation, or the need for fire suppression system. All depends on your risk assessment and insurance policy. The second benefit of esters, why people use them, is because they are biodegradable, readily biodegradable, meaning they have less impact if you have a spillage in the environment from a transformer or during shipment. A mineral oil is not biodegradable at all, and so once you have a spillage, it will be sustained in the environment for a long time, and so expensive cleaning procedures are needed to reduce the impact. On the other hand, MIDEL esters, or esters in general, are readily biodegradable, both the natural esters and the synthetic esters, and so they can allow reduced bondings and reduced procedures for cleanup in case you have spillage with minimized risk on the environment. Another item here I thought to share, and I will talk about it later more, is the breakdown voltage. Of course, these fluids are dielectric fluids. Their main purpose is to create this insulation within the transformer. Under AC conditions for this test, esters and mineral oil are comparable in behavior, and so we expect the AC breakdown voltage to be higher than 70 kV in normal application and in a transformer. And finally, I wanted here also to highlight the oxidation aspect of these fluids. Mineral oil is known to be oxidation stable, and also synthetic ester, MIDEL 7131 here, is also an oxidation stable. But natural esters, as I said earlier, it's only be used in sealed units, hermetically sealed units, or with rubber bag, where we can guarantee there's no exposure of the liquid with air. Otherwise, you would have oxidation. Oxidation can lead to high acid value and to higher viscosity, and then higher temperatures, and then could be failure. So I only touched based on 4 aspects here: is the fire, the biodegradability, breakdown voltage AC, and the oxidation. Now, to give you more sense of the fire aspect, this is 4 images you can see here of a test we conducted by filling a pan with the liquid. So the top 2 pictures are for mineral oil, the bottom 2 pictures are with MIDEL 7131 synthetic ester. And the idea here with the pan, we inserted a thermocouple to measure the average liquid temperature, filled the pan with the liquid, and then exposed the pan surface to an external flame, an oxyacetylene torch. Now, typically the flame temperature is 3000 degrees. Now, for mineral oil, if you look at the top left picture, for mineral oil, after 3 minutes, the bulk liquid temperature reached 95 degrees, and then you started having localized ignition, a small flame, after 3 minutes. Further 1 minute more, the entire pan catches fire, as you can see in the top right picture. And this is burning fiercely with heavy smoke. Now, the bottom ones are for equivalent scenario with MIDEL 7131 synthetic ester. The same amount after 3 minutes. We expose this surface of the liquid to the oxyacetylene torch. After 3 minutes, the bulk liquid temperature reached 100 degrees with no localized ignition. Further 70 minutes more, with even the bulk liquid temperature reaching 230 degrees, you still don't have any localized ignition. So I thought to share this as a simple test to indicate why is the K-class classification indicate that these fluids are less flammable, and so create or allow the users to reduce the spacing between them, reduce the risk of fire if you are using esters, K-class esters in your transformer. Now, the other aspects of esters, as I mentioned, is the readily biodegradable status. And here I thought to share with you the curve, and this is based on the testing method. At the bottom, you can see OECD 301 for biodegradation. On the x-axis of this chart is the test duration. Usually the test lasts for 28 days. On the y-axis, you see the biodegradation percentage. And here you see 3 or 4 liquids: natural ester, synthetic ester, mineral oil, and silicon liquid. You can see mineral oil and silicon liquid will not biodegrade within this test to more than 10%, so very low, so they will be sustained in the environment if you have spillage. On the other hand, natural esters and synthetic ester can reach biodegradation to more than 85%. And so this allows, as I said, reduced funding and reduced procedures for cleanup if needed, if spillage occur. Now, leaving these basics behind us, now we got to know a little bit more about esters, the fire safety features, and the biodegradability. Let's look a little bit more in detail for the aspects of design, especially for power transformers with esters. And the first thing I will only consider here 2 aspects. The first one is the electrical design aspects, and then the thermal design aspect. For the electrical design aspects, we know that these transformers are filled with the liquid. The liquid is a dielectric fluid. Now, any dielectric material, dielectric fluid, has a permittivity parameter. And the permittivity parameter contribute to how the electric field, electric stress, is distributed within the insulation system. So here we show an example to how the change in permittivity of the liquid can alter how the stress is distributed between the insulation material of the transformer. We know that the insulation material of the transformer are composed from paper and liquid, breastboards and liquid gaps. So in this, let's focus first our attention to the table. You see mineral oil and synthetic ester. Underneath it, you have the fluid permittivity. For mineral oil is typically 2.2. And if you impregnate paper with mineral oil, the composite system has a permittivity of 4.4. Comparing this with a synthetic ester, the fluid permittivity is higher than that of mineral oil, 3.2. And then you have the paper impregnated with synthetic ester, the permittivity is 4.7. Now, let's shift now our attention to the figure. On the right-hand side, you see the example there. Basically, you have two rectangles. One is the breastboard and one is the liquid. So because of the permittivity difference, the electric field stress is distributed proportionally between this solid breastboard and the liquid. Our interest in a transformer is to reduce the stress in the fluid gap and increase the stress in the solid impregnated insulation because the solid insulation is stronger than the fluid. And back to the table now, we can see for mineral oil, if we do the calculation, as you can see in the example, you can see in the fluid stress is 17.6 kV per millimeter because of the lower permittivity, 2.2 in the oil gap. And comparing that with the synthetic ester, you can see there's a reduced stress in the oil gap to 15.7 in the table, the green one. And so this will give an advantage when using esters in a transformer because it will reduce the stress in the oil gap compared to the solid insulation. But here we need to take care as well because of this change in permittivity, the entire stress in a transformer will change and some location will have higher stress. I will talk about this in the next slide. So the significance, as a summary, the significance of this change in permittivity, that esters give an advantage in creating more uniform distribution of stress field in liquid paper interfaces. Between the interface, you have a lower stress. But also we need to take care, should be taken care when assessing the stress distribution within the transformer when we are designing with a synthetic ester instead of mineral oil. And to clarify that further, we can look at this simple system for a transformer. Now, this is a general slide to talk about how we assess the stress distribution within a transformer, and then we can appreciate the impact of the liquid on that. So on the right-hand side, you see a transformer schematic. You see the high voltage winding, the low voltage winding. Between them, you have oil gaps separated with breastboard barriers. And you can see point A and point C, and then we have a dashed line, which is the stress line from point A to point C. Our interest usually is to really know where is the highest stress, usually at point A, and making sure when we design for a synthetic ester instead of mineral oil, our stress at point A will not exceed the strength of the insulation. And this is more explained in the left-hand figure. In the left-hand figure, you can see on the x-axis oil gap and then breastboards, solid insulation, oil gap, and breastboards. And this is from geometrically from point A to point C. On the y-axis, you have two lines. One is the stress and one is the strength. If you look at, I hope you can see my mouse. If you look at point A, you have two lines here, line the stress, and then the other line is the strength. And our ideal thing is really, as a designer, to estimate the safety margin here. And when we are using a synthetic ester, this safety margin can reduce, and so sometimes a failure is caused. So with this, I hope to give just an overview of the impact of a different liquid on the transformer design. Now let's talk a little bit more about the thermal, because we know esters have different viscosity than mineral oil, and so they can contribute to higher temperatures. And so I thought to share some basics here. So for to assess the transformer thermal modeling or performance, usually we can look at either the steady state processes or the dynamic processes. When we talk about the steady state processes, this is the temperature rise test in the factory after we design the transformer to devise a hotspot factor, which help us in estimating the hotspot temperature, which is the critical temperature in a transformer winding when the transformer start accelerated aging. The dynamic side of the thermal modeling is really dependent on the power system viewpoint. So you can have dynamic loading because of extra electric vehicles on the grid or solar panel generation, and so could lead to short-term overloading. Once we look at these two, either steady state or dynamics, we need to know what is the transformer cooling mode. So natural cooled transformers are different from directed cooled transformers and forced with pumps. So when we talk about thermal, we need to understand, are we talking about steady state? Are we talking about dynamic? What is the cooling mode of the transformer? Is it natural cooling or directed cooling? The last layer, the bottom ones, are then the contributing factors for the temperature distribution within the transformer. The first one on your left-hand side, you have the loss distribution. This is the uniform losses, I²R, DC losses, and also the non-uniform losses, the eddy current losses within the winding. And then the middle one is the winding geometry. This is the designer. So distribution transformers differ from power transformers. Is it disk type winding or layer type winding? And then all depends on how we rearrange our cooling ducts within the transformer. And finally, the right-hand side, we look at the heat transfer conditions. So how fast is our liquid flowing, the flow speed, the thermosiphon forces in natural cooled transformers, how many radiators we have, and what is the typical operating liquid temperature and ambient temperature. And finally becomes the liquid itself, the liquid parameters. You can see it in red there. This is the dielectric fluid properties. These are the viscosity, specific heat, density, and thermal conductivity. My aim in showing you this slide is really to build that overview understanding of the thermal modeling and how the liquid, where the liquid falls in the entire picture. And to give more understanding on the liquid, if we focus more, the main parameter that contribute to the cooling ability of the liquid is the viscosity. Esters are known to have higher viscosity than mineral oil, and this is actually the reason why they are having high fire point. So they are fire safer, K-class. But as you can see, it depends where you are operating. Above 60 degrees, the difference in viscosity between esters and mineral oil is reduced. But for cold start, we need to take more precautions, either in our transformer design or operation to deal with that. But to give more numbers now, instead of talking in general, let me share with you some published cases for simulation to show. One is simulation, one is practical aspect of what we expect of the temperature difference between mineral oil and synthetic ester. So in this slide, you can see an example from a published paper. The reference is below. And here we're using computational fluid dynamics, CFD, to really estimate the flow distribution within a disk type transformer and the temperature distribution. The researcher there compared mineral oil, synthetic ester, and natural ester. And what we focus here is the hotspot temperature. Of course, just to clarify the images, these are one pass in a disk type transformer. You can see here the desks, and between them you have cooling ducts allowing the liquid to circulate and cool them. You can see mineral oil, the hotspot temperature is 70 Kelvin rise because it has lower viscosity than esters. And if we look at synthetic ester, the hotspot is 77 K, so 7 degrees higher than a mineral oil. And then you have a natural ester 80 K, 10 degrees higher than a mineral oil. Now, this difference in temperature is not universal for all transformers. It depends how big is your transformer. This case is for a power transformer, so we do expect this increase, especially at under natural cooled conditions. So this is one example, and the other example is really a practical one. So here the researcher retrofilled a 3050 MVA transformer, 141 kV, 13 secondary, on an or on-off transformer, and then measured the top liquid temperature and the bottom liquid temperature. These temperature values of that experiment is shown in the table. So let's focus now on the table. You look at the first column, the temperature rise above ambient. The first row is the bottom oil temperature rise, and then the top oil temperature rise. Under the 30 MVA, which is the loading, you see mineral oil under on-an and natural ester under KN-AN. So the bottom oil temperature for mineral oil is 40 here, for natural ester is 33. Whereas the top oil temperature for mineral oil is 52, for natural ester is 53. You can see the difference. You have reduced bottom oil temperature and higher top oil temperature. And so total temperature rise is higher from bottom to top under natural esters compared to mineral oil. In this case, only top liquid temperature increased with 1 degree because it's 30 MVA. The same transformer now, if we increase the loading to 50 MVA, the top oil temperature increased from 50 under mineral oil, as you can see, to 56. So in general, and this will lead us to the next section, which is the retrofilling. Once in general, we expect the top oil temperature with an ester to be 4 to 6 degrees higher than that of a mineral oil for the same design. And I must emphasize here, this really depends on on the transformer size, on the transformer loading, on the winding type, as I reviewed in the first slide here for the overall performance. Now, so far, if I just summarize what I've been talking about, now I introduced esters, the key benefits of fire safety and biodegradability, and how they compare in that table with mineral oil. And then we reviewed really basics on the transformer design aspects, electrical design aspects, or thermal design aspects. I mentioned that the electrical design aspect, the most important parameter to consider is the permittivity, which will alter how the stress is distributed within your insulation system if you are using an ester instead of mineral oil. And the last one is the thermal design aspect. It's a global picture of the transformer, and the liquid is one contributor to that. For the same transformer, we expect a hotspot temperature for a power transformer to be 7 degrees higher than that of a mineral oil, and the top oil temperature to increase by 6 degrees. Now, this is the summary. Now, to go to the application side is retrofilling. Now, end users may end up with a decision depending on the changing circumstances, either to buy a new transformer or to use other technology like esters to utilize that asset and benefit from the fire safety and biodegradability. So in our grid, we know we sometimes have aging assets, aging transformers, or these transformers are located in sensitive areas, or the power demand is increasing. And then because of all of these, we need to maybe installing new fire suppression systems or alter our civil work in the substation, adding firewalls or fences or creating clearances. This is for an existing unit. Now, if we are in a situation like that, when you retrofill that transformer with an ester, you increase its fire safety. You may increase business continuity, so reducing the probability of failure and power cut. And also, by retrofilling, you can satisfy the insurer. Sometimes insurers come and ask that you need to use a less flammable liquid K-class fluid in that transformer. And of course, finally, with retrofilling, you can reduce the environmental risk if you have a spillage in that location. So as an asset manager, you will end up with a choice. Either you can buy a new transformer, or based on certain assessments, select that transformer as a good candidate for retrofill and conduct the procedure. And the aim of this short section is to indicate how we select a transformer as a good candidate for retrofill, and also what is the procedure for retrofilling, and finally, how do we manage our transformers when retrofilled with an Ester. Okay, so to really select a transformer as a candidate for retrofill, we need to look first on the voltage class. So usually distribution size transformers, any transformer lower than 33 kV, we do not expect any issues with the transformer if we just replace the fluid. Because these transformers, they do have lower stress in general in them, and so the insulation is based on mechanical strength of the winding. And so if the transformer has higher voltage class, higher than 33 kV, then please consult with us, because we need to review certain things to assess if this transformer is a good candidate for retrofill or not. Another aspect, of course, is very important, is the on-load tap changer. We know that the on-load tap changer is a critical unit to regulate the voltage of the grid, especially with increased solar generation, power generation. And so the on-load tap changer, because it's a mechanical movement and esters have higher viscosity, we need to assess if the on-load tap changer is suitable for a retrofill, or we can keep it with mineral oil if it's in a separate tank. And of course, finally, once we assess that this is a good voltage class, we ask the user to take samples, DGA samples of that transformer. Best is 2 samples prior to retrofilling. Assess what's the forerun analysis and DP value of the paper, the insulation material inside the transformer. If the transformer is too old, we do not really, usually recommend retrofilling it because the user will not really benefit or utilize the investment there. And worth emphasizing that esters, though they slow down aging mechanisms in the transformer, they will not fix the paper. So if the paper is too old, then unfortunately it's too old, and perhaps buying a new transformer is the right option. And finally, for retrofilling, we need to consider what is the original liquid. And this is the miscibility guidelines. So usually if you have in that transformer mineral oil or any other ester, natural ester or synthetic ester, you can retrofill with an ester. But if that transformer has silicon liquid, we cannot retrofill it because silicon liquid and esters are not miscible, and they will not mix homogeneously. So once we identify that a transformer is a good candidate, then we go through the procedure of retrofill. And this slide shows you 5 steps, basic steps. Of course, first and foremost, we work safely and we follow proper procedures in terms of risk assessment and good conduct. And the first item, as you can see here, is the drain. Once everything is safe, we start removing the original liquid from the transformer. This is a draining. And our aim here is to drain as much as we can from that transformer of the original liquid. To aid our draining efforts to remove as much as we can from the original liquid, we start rinsing the winding, which is the second step. Usually we recommend or give guidelines to rinse with 10% of the transformer volume with hot MIDEL or hot ester. Elevating the temperature of the ester will reduce its viscosity and allow it to go through these cooling ducts within the transformer, removing sludges and clearing mineral oil as much as we can. This is the rinse process step. And then the third step is dripping. Then after we rinse, we allow the transformer to settle and drip for 2 hours. This will aid us in removing as much of the residual mineral oil as possible. And then the fourth step is basic refilling. Of course, we refill through a filtration machine where there's an inline heater increasing the temperature of the liquid, aids in removing bubbles, air bubbles, preventing them from being trapped within the transformer. Once we do 1, 2, 3, 4, and the transformer is filled and settled, we do testing. We take samples from the transformer we measure the breakdown voltage and other parameters to make sure that this is now a successful retrofit. These are the 5 basic processes and steps of a retrofit. Now, of course, as we are doing this, we may observe leaks or remove gaskets. So better to use a new gaskets as you are doing the job now. It's better to fit new gaskets to prevent any further leaks. And of course, some utilities will measure insulation resistance, mega test. And worth mentioning here that esters have different chemical structure than mineral oil, so the insulation resistance will be lower naturally for an ester filled transformer compared to mineral oil. And the table in front of you shows just that. For a distribution size transformer, a mineral oil filled one could have an insulation resistance 10 gigaohm to 15 gigaohm. If filled with synthetic ester MIDEL 7131, could be 15 times lower, so 0.5 gigaohm to 1 gigaohm, and for natural ester could be 1 gigaohm to 2 gigaohm. These are typical value range, and I wanted to show them here to, so that anyone doing the retrofill and measuring will not be alarmed by these lower values compared to mineral oil, because usually lower values will indicate a change in the insulation within the transformer. Of course, after retrofill, I mentioned we take a MIDEL or a ester sample. We check the breakdown voltage, the moisture content, and the acid value. These should be within the in-service limits, which I will talk later. And best practice, when you retrofill a transformer, you need to identify it differently so that no one else's will come and top up with mineral oil, and so defy the purpose of a K-class. And sometimes you can color the transformer differently or mount a plate identified with the retrofilled liquid and the date of retrofilling. And of course, once you do the retrofill, you need to assess continuous maintenance of that transformer. And for that, we need to educate our maintenance engineers of what are the differences for the in-service limits between mineral oil and esters. In the table in front of you, you can see 3 or 4 parameters. These are the basic parameters to check. One is the breakdown voltage. Esters and mineral oil are equivalent in that term, and the breakdown voltage should be higher than 30 kV. The moisture content, mineral oil is very sensitive to moisture, so it will not tolerate any moisture above 30 ppm. Then you need to do maintenance on the liquid. Esters have a different story. They can tolerate much higher moisture content without reducing the breakdown voltage. And I will focus on this later. So in this table, the moisture content for in-service for synthetic and natural esters should not exceed 400 ppm for a retrofilled transformer. And also the acid value, as you can see, mineral oil has different limits from esters. I want to focus here on viscosity. Mineral oil and synthetic ester, we don't expect any viscosity increase as it ages because they are oxidation stable. Natural esters, you may observe increase in viscosity, and if this increase become more than 10%, then you need to do action because you have a severe oxidation processes happening. And finally, once you finish this retrofill, you can mount a new breathing cartridge to make sure the transformer or the liquid is not wet. You can leave the transformer to stand for 24 hours or 12 hours before connecting to full load. Usually before connecting to full load, we ask to connect 3 hours at no load. This will aid us in heating the liquid, removing any air bubbles from the transformer to the external. Now, to summarize this section, now transformers with voltage class lower than 66 kV, they are potential for retrofilling, and so we can do assessment on them or help you do the assessment, especially the on-load tab changer and the paper condition by taking a liquid sample. Retrofilling can be a good option for utilities if you have high moisture problem in your transformers, always wet. Esters tolerate more moisture, and so you can reduce your maintenance periods, and so eventually save money. Sometimes the standards changes, so you have to have a K-class fluid in a transformer to increase fire safety, and then retrofilling can offer you a solution either to meet the insurers or the environmental regulators. If a transformer is now becoming located in a high fire risk area, say urban area where you have a shopping mall, a lot of utilities now choose to retrofit to reduce risks of fire and so fatalities in human and business interruptions. And this will, for sure, for a utility, show that it has social responsibility. And one aspect I will talk about as well, that esters are softer on the paper, so actually they can prolong the life of the transformer when retrofilled. Okay, with this, we can move to the, I think, the fourth section of this presentation, which is regarding the maintenance of esters and testing. So when we talk about maintenance, I thought I split this section into two. The first one, let's focus on the liquid, how we maintain the liquid, and the second one, how we maintain or assess our transformer filled with esters. So the first one is the liquid condition assessment. For this, we really need to appreciate the difference in chemistry between mineral oil and ester liquid. So mineral oil is a hydrocarbon oil derived from crude petroleum oils, and so it can compose from different molecular structures, paraffinic, naphthenic, aromatic, and so on, in different ratios to provide certain parameters. But basically, the main building blocks of this mineral oil is hydrogen and carbon, so it's a hydrocarbon. Anything produced from mineral oil due to a fault will be based on carbon and hydrogen. Now, if we look at esters, they have a different building block called the ester linkage. You can see it in front of you. This ester linkage or molecule is a carbon with double bond with an oxygen molecule, and then you have single bond with oxygen. And then the rest of it is a hydrocarbon chain similar to mineral oil. The R and R prime, basically hydrogen and carbon. So once we understand this difference in chemistry, now we start really comprehending why esters have different in-service limits, one, and also the DGA will be affected too, which I will be talking now on. So for the in-service limit, one of the key parameters is the moisture tolerance. So in this here, we justify why esters can have high moisture content without really breaking down, reducing the breakdown voltage. You can see the basic ester structure here really is a polar structure, so it has a slight polarity, and water structure is also a polar structure, has a slight polarity, and with both of them together, they can bond like a clip, like a magnet in a hydrogen bond, not a permanent bond, but this allows the esters to dissolve or absorb more moisture in them, so have high saturation levels. And this is the basic or the fundamental explanation. And now we can look at the breakdown voltage, because the breakdown voltage is one of the basic parameters we check to assess our transformer. And on the chart in front of you, you can see on the x-axis is the moisture content in ppm, and on the y-axis you can see the breakdown voltage. Of course, you can see 4 liquids here, the mineral oil, silicon liquid. You can see MIDEL EN1204, which is a natural ester, and you can see MIDEL 7131, which is a synthetic ester. Mineral oil is very sensitive to moisture, as we know, and so any slight increase in moisture, the breakdown voltage will drop sharply. Silicon liquid is slightly better than mineral oil, but it still is a sensitive one to moisture. Now, because esters have these ester groups I mentioned, natural ester has the 3 ester groups, and so they can tolerate, say, moisture without dropping the breakdown voltage up to 300 ppm, which is a huge significant increase compared to mineral oil. But the best one there is the synthetic ester. You can see you can reach up to 600 degrees moisture content before the breakdown voltage starts to drop. And this really facilitates, one is we need to know what our in-service limits for both the breakdown voltage and also the moisture content and the acidity. When are we using esters compared to mineral oil? And where education is very important for our maintenance engineers. Now, for education, we need to be familiar with the relevant standards for in-service limits. In front of you, I thought to share with you the references. On the left-hand side, you have the synthetic ester, the IEC 61003. Now, this is a standard made in 1992. It's a little bit old now and being reviewed. I think in the couple of years ahead, we will have a new one. In the table, you can see the classification of ester in service. This is also applied for voltage levels 35 kV and below for this standard, and you can clearly see the parameters to check are the appearance, the water content, neutralization or acidity, breakdown voltage, dissipation factor, and the fire point and DC resistivity. These are for your reference, I thought to add. And equivalently, you have a natural ester standard, the IEEE C57147. And equivalently, depending on the voltage class, you have different in-service limits. And so we need to familiarize ourselves with the differences for in-service limits between esters and mineral oil. Now we go to how we assess a transformer filled with an ester through a DGA, because DGA is one of the main tools we use to spot faults in a transformer. And again, we need to emphasize the difference in chemistry. Esters have different chemical structure than mineral oil. Now, in front of you, we start with mineral oil. It's a hydrocarbon, so any fault will decompose this liquid to produce gases, DGA gases, such as hydrogen, methane, ethane, and ethylene and acetylene. This is for mineral oil. For an ester, you have these ester groups, the oxygen, as you can see within the square boxes, and any fault, you will decompose this fluid to hydrogen, methane, ethane, ethylene, acetylene in similar way as to mineral oil, but also you will add carbon monoxide and carbon dioxide. So these are the key differences between mineral oil and ester. You have these carbon oxides produced from faults involving only the liquid. Now, DGA with esters is still very similar to that of mineral oil. You know, in DGA, we emphasize one is we need to observe the trending. Second is we need to have good sampling procedures, so to prevent any contaminations. And so in esters, we follow the same procedures as mineral oil. And there are key differences between esters and mineral oil. These are, the first is the gas solubility, because esters have different chemical structure than mineral oil, so gases will be soluble in different ratios or percentages. Also in tools, the amount of gases produced can indicate different fault levels. In esters, we have carbon oxide production because of that ester linkage. And also sometimes in natural esters, you have stray gassing initially after the heat run test, because they have unsaturated bonds which oxidize with dissolved oxygen. So you can produce ethane. Now these are the key differences, but still we have a lot of similarities. You see in the table here, for esters and mineral oil, a fault category such as partial discharge can be indicated by hydrogen. Now if you have hydrogen and methane, can indicate discharges of low energy. If you have acetylene, always indicate discharges of high energy. And then finally, if you have methane, ethane, ethylene, you can indicate a thermal fault. On the right-hand side of this slide, you can see the Duval triangle, and I'm sure a lot of you are familiar with it. The Duval triangle, basically, we do have Duval triangles for esters equivalent to that of mineral oil. We just need to use the right one when we interpret. So the Duval triangle basically relies on the percentages of methane, ethylene, and acetylene in this geometric presentation. And once you take the DGA, plot it here, you can guess what kind of fault in the transformer causing these gases. So this is the DGA, and I thought to share with you one example of a lab test results where you can see on the left-hand side is mineral oil, the right-hand side is a synthetic ester. Now this is a test conducted under arcing conditions. And so on each of these charts, you can see on the x-axis the key gases: hydrogen, methane, ethane, ethylene, acetylene, and carbon monoxide. And on the y-axis, you see the combustible gases percentage within that test. So you can see mineral oil is really almost the pattern of gases is equivalent to that of a synthetic ester, with two observations differences. One is synthetic ester, you can have more carbon monoxide compared to mineral oil, and the other observation is actually the volume of gases produced in synthetic ester from a fault is slightly lower than that produced in a mineral oil. So these are the two key differences, and at the end of this slide you can see the key references for DGA. I advise, if you are interested, to look at the IEEE C57.155 and also the SAIEE working group or the brochure report 443 for DGA in non-mineral oil liquids. So with this, I will transfer or go to the, I think, the fifth section of this presentation, which is the benefit of esters to asset managers. And really, this is as I say, the time is running out, and so we only touching very basic on this. And I want to remind you here before going into this is that esters, I mentioned, they have different chemical structure compared to mineral oil, and so they can tolerate high moisture content without reducing the breakdown voltage. Now, for asset managers, what we are concerned is how, when our assets will fail, and how we can devise replacement strategies, or if we can really extend the life of our assets without buying new ones. And so esters, because they can tolerate more moisture, they can aid in reduced maintenance periods to go check wet transformers and sending your engineers. This is one aspect that asset managers can benefit when using esters. Now, the second point on the slide, you can see a snapshot from the SAIEE brochure 323, Aging of Cellulose in Mineral Oil Insulating Systems. And this talks about hydrolysis as an aging mechanism of paper. Now, in the underlined with red, it indicates that a new transformer will have a wet paper, usually 0.5% only, but then as it ages, the paper wetness will increase to 5%. With this increase, you can accelerate the aging rate of the paper, and so the asset will live shorter. What esters can contribute here is they can keep the moisture out of the paper, especially synthetic ester, and so keeping the paper drier relatively. With a drier paper, the paper will live longer. And so asset managers can benefit from extending the life of the assets when, say, retrofilling a transformer, which is wet transformer. The ester can dry that transformer a little bit more, I mean the solid insulation, and aid in extending its lifetime. Though I was wishing more time to show more detail on this, so I thought the one representative curve to show the impact of esters on extending the lifetime of the transformer is this curve. This is taken from the IEC 60076-14 for high temperature insulation material. On the x-axis, you see the temperature, operating temperature, and on the y-axis, you see the unit of normal paper lifetime. 1 here, meaning that the paper will live its expected lifetime, say 20 years. And on this chart, you see two graphs. One is in blue and one in green. You have the kraft paper, the blue one in mineral oil, and the green one, the kraft paper in natural ester. For a nominal lifetime for mineral oil and kraft paper, the hotspot temperature, the high temperature in the winding, should not exceed 95 degrees based on this curve. But if you are only filling with an ester, with a natural ester, you can reach up to 110 degrees and getting the same lifetime of the transformer. Equivalently, you can keep running at lower temperatures, 95 degrees, and then go vertical on the curve to extend the life of the transformer further. Now the curve here shows 5 times more. At MIDEL, we only indicate that you can, we are conservative, and so 20% or 30% more lifetime out of the transformer, not 5 times. So for asset managers, esters can really contribute to, as we can look at this chart, I'm starting with the left top one, reduce substation footprint, because esters are K-class fluids, and so they allow reduced spacing between the transformer and the surrounding. Also, esters are, they are readily biodegradable, so they reduce the impact on the environment. They can enhance the life of the assets, increase its reliability, as I showed, by making the paper drier, and so the transformer can live a little bit longer. And so definitely esters will can return the cost of investment to the users, which we will talk in the cost section later. So I sense I'm maybe a little bit running out of time, so good, we are reaching almost the end of our webinar. This is the 6th section, which is the case studies. And here I show 2 cases. One is a power transformer and then of a retrofit. So this is the picture in front of you. This is a natural ester filled transformer, is filled with our canola-based natural ester MIDEL EN1204. This transformer is a huge one, it's 420 kV, and this is produced in 2019, very recent. In this transformer, it used 100 tons of the liquid, and this is made from local crops. So the utility requesting this transformer, one of the requests is that they use a local harvest or local crop, and so they used the MIDEL EN1204. And one aspect the utility decided to use this liquid is because MIDEL EN1204 one has lower pool point, so it can operate to -31 without any issues. Especially in Europe, you have this high cold temperatures, and also it has, as a natural ester, it has double the oxidation stability of MIDEL, say, EN1215, which is our soybean-based natural ester. So the preferred option is to use MIDEL EN1204. And this is the utility is a Transit BW, which is, I think, a German utility, transmission utility. And we know this indicates that these utilities are using a very high natural esters in a very high voltage transformers, indicating that the technology is maturing more and more by the year. This is our first case study. The second case study as well for retrofilling. This is a utility called Vattenfall in Germany. And so in the 1992, they started this program of retrofilling key transformers located in sensitive areas or water protected areas in Berlin. And they wanted to use a readily biodegradable fluid, which is also oxidation stable. They used MIDEL 7131 synthetic ester. And so from that time, these transformers are distribution size transformers, typically 400 kVA to 600 kVA. And from 1992 up to now, they retrofilled more than 5,000 transformers with synthetic ester. So again, this case study aims to show that this technology is maturing, is well adopted within the industry, and if it's the right in the right application, in the right sector, it can really add value to the asset managers. And so this is also a short, a snapshot of our reference list. For power transformers, you can see here synthetic ester and natural ester. As I say, these are just examples with high voltage ranging from 110 kV, 151 kV, and proceeding to 400 kV. both the synthetic ester and the natural esters are evolving in that range, becoming more and more applied in power transformers. The latest ones is in the 2020 and 2019. At the end of the table, you can see 400 kV transformers. One is 315 MVA and the other is 400 MVA, 440 kV. So this just to give the perception that this is not really a new technology, it's maturing, and the manufacturers are now well able to design high voltage transformers with natural esters. Now almost the final section is the cost, which I will go here also briefly. So you have the distribution. One example is the distribution transformer. Of course, esters, because they offer this K-class, less flammability and biodegradability, they cost more than mineral oil, initial cost of the liquid. And so this can be reflected into the transformer. So for a distribution size transformer, we expect a synthetic ester to be 20% more higher cost than a mineral oil one, and a natural ester can be 10% more. This is one example. It depends how you optimize the design. But because esters are K-class and readily biodegradable, in the installation, you may not need containment. This is the second row there. So you have reduction in cost in the total cost of installation because you have a reduced containment and footprint of the substation, and also in the total cost of the substation because of the safety area is reduced. So with this example, we can see at the end of the project, compared to mineral oil, a synthetic ester can achieve lower cost by third, 31, minus 31, and natural ester is equivalent minus 33. So this, of course, so what I encourage here is, instead of looking at the liquid cost only, you need to look at the project cost, at the total project cost, and then assess also the other benefits which you can gain by using esters instead of mineral oil in certain applications. Another example here for a power transformer. Again, in a power transformer, the initial cost of the transformer for a synthetic ester can be 20% more than a mineral oil. Natural ester can be 14% more than a mineral oil. But for these big units, usually you can get rid of certain installation like the fire suppression system and the space of the substation, so reducing cost there. Also, the maintenance of the fire suppression system for 40 years can reduce there when you are using an ester, and the base containment. So overall, you can achieve actually lower cost than a mineral oil by 27 reduction, or 30% percent reduction with natural ester or synthetic ester. Okay, so as just a brief summary, so esters are now been used since 1970s in power transformers, in distribution size transformers, in all aspects and sectors of the power and electricity grid, ranging from very cold weathers like in Russia, Siberia, to hydropower station, to deserts like in Kuwait City, where to minimize and reduce fire risks. Undersea, even in oil extraction, sometimes you have transformers there. Wind turbines, of course, esters are used there to lower the maintenance requirement, and in distribution size transformers. One example here, you can see the picture with these blue barrels. These are Actum made to Eskom in South Africa. I think is more than, if my memory serves well, 6,000 transformers now in the country. And so also esters are used in the fast high-speed trains. There's one case study I don't have time to show, is the Highbury substation in London, where they filled these big units, 400 kV units, with synthetic ester. So with this, I end my presentation. I hope it was informative for you. I very much welcome any feedback or question, and I hope you enjoyed it. With this, I give you back, Jay.
Okay, everybody, it's Richard here. I'm going to just be handling the question and answer session on behalf of Jay. And then Jay will close with the thanks on behalf of the SAIEE. So without further ado, I'm just going to go through some of the questions that we have. There are also some comments. I'm going to start just with some of the easy questions and then work through them. There are probably about 7 questions here. The first one is, are we prepared to share the presentation? The answer is yes. The presentation will be published on the SAIEE website. Jay will talk more to that in his close. A question here from Rob Lloyd. Does the ester, once refilled, have to be taken offline and filtered under temperatures as with mineral oil transformers?
So if I understand, the question is if we can treat the liquid in a similar way as mineral oil through filtration.
Does it need to be, yes, does it need to be filtered?
Oh yeah, what we need is to first assess the liquid condition. So it's in a similar manner as mineral oil. If you have high moisture content in the ester, we need to filter it, vacuum dry it, and so it can be under the same procedures of filtration as mineral oil, but usually we don't need to, only if the in-service parameters indicate so.
Okay. This was a question, if I retrofill, say, a 132 to 11 distribution transformer, do I need to make it a sealed type transformer and separate the online tap changer? You did answer that question to a certain extent, but would you like to just maybe clarify it?
Yeah, I think it's a very good question, but I want to first indicate that 132 kV transformer, usually at MIDEL, we don't really indicate that this is a good candidate for retrofill because of high voltage. And I indicated that because of this permittivity change, the stress in the transformer will redistribute, and so you may have a failure. So, but also the question is very good because yes, we need to look at the entire project. So if you are retrofilling with a natural ester, you need to look at if it's a breathing transformer, then you need to seal it. This will increase the cost. Then your option is to use a synthetic ester instead because it's oxidation stable, and so on. So
yes.
Yeah, I hope I gave a little bit more detail, but as you said, it's a lot of the information is in the presentation.
Yes, I did. There was a slide where you indicated that you're typically looking at 66 kV and below for this sort of retrofitting action. Is that correct?
Yes, yes. So I think it's one aspect for this 33 kV or 66 kV in the States, in the US, they use higher safety margins in the older designs, and so sometimes older transformer can be retrofilled up to 66 kV. But in Europe, say they adopted CAD design, and so they reduced the safety margins. And so in Europe, we are more conservative. We say up to 33 kV. But yeah, so this is within the range. 66 kV is within the range.
Yes. The next question is, who are suppliers of ester in South Africa?
Well, I'm not, so being technical, I think this question need to be directed to my colleague Victor. If the one who is asking this question can contact the local, our local, but we are supplying, our company is supplying there, but I don't know if we have a distributor there. To be honest, I'm technical, I'm not aware of it.
There was a question between the difference between a dry transformer and an oil transformer. I'm assuming that's the difference between a resin cast, a dry transformer, and an oil transformer. Possibly, I'm not too sure how to interpret that question.
So I can add a sentence or two because this is also very good, let's say, comment or question. So esters are K class, so they enhance the fire safety of the transformer, reduce the fire risk, and also cast resin transformers doing that. That's why people use them. And so, but cast resin transformers can have high no load losses in them. Maintaining them is a bit tricky. You need to keep them clean from dust, also PD measurements, and esters can offer an equivalent solution in terms of fire safety. If that will add anything into the comment or clarification.
That's a very good response. Now that it's nice to know there is an alternative to dry type transformers. What is meant by thermosiphon forces? I think it's somewhere in your presentation. Yes.
Yeah. So I apologize, I couldn't describe it more, but thermosiphon forces basically is the forces which caused by difference in density. So example is a hotter air will go above and cooler air will come down. This movement is caused by the thermosiphon because with change in density, the liquid in the transformer, because of change in density, under natural cooled transformers, the liquid will go up the tank, and then the warmer liquid will go up, and then the cooler liquid will go down. This will create a circulation, and this is the thermosiphon force.
Okay. The next question is actually a statement from Muhhamad Khan. He has actually, unfortunately, had to leave the meeting, but basically it's just a statement that in terms of the classification of ester oil transformers have not been classified by the Department of Environmental Affairs in South Africa. And so for now, until that classification occurs, the same cleanup regime needs to be implemented. So that issue of the biodegradability of ester hasn't yet been ratified by the South African legislation.
So I think one thing is really, I mean, I understand the comment, and this is part of it. Is our job at MIDEL is to educate these authorities and agencies, and this is not just in South Africa; it's globally. So the movement is going there, but one aspect is to recognize is that with an ester, with a readily biodegradable ester, if you have a spillage, the impact on the environment is really reduced, so cleaning up will be lower. Even if you don't change the substation for bonding reduction, if your statistics indicate you usually have leaks, with an ester you will have lower impact, and so showing that responsibility, showing that reduced impact on the environment, even with no change in regulations.
Okay, it's a question from Adesh. One of his clients, I'm not going to name the client, the insurance company has requested that 132 kV transformers be retrofitted with ester. So now we've just heard that the 60 kVA limit applies. Is there any supporting information that we can go back to the insurance company with and tell them that this is not a viable solution?
So this is So I mean, with how we can support is to show the reason why this is the limit, and by sharing published data on the electrical behavior or breakdown mechanisms of esters versus mineral oil, and that's why we don't think 132 can be simply retrofilled with another liquid ester. But this can be a project, and so the user need to assist whether consulting with the manufacturer of that unit. You can do some change in the insulation inside the transformer so that to allow it to become more ester acceptable to an ester, say. But that's the best we can offer, is to either give information on the differences between esters and mineral oil, and so the one who asked the question can share that information with the insurer, or they need to consult with the manufacturer to see if they can adopt the transformer internal design to be suitable for an ester.
Yes, I was actually paying attention to your presentation in the slides, and I saw that the impact of the high hotspot temperatures, and especially under overload conditions, that's where the vulnerability stress increases. Yes. The next question is, it's also quite a nice question. If sitting with a sort of 2.5 MVA transformer at 11,000 volts, step down, what, they've retrofitted the transformers with natural ester, but they don't really have a good indication of what a typical oil temperature settings and winding temperature settings would be. Do you know that off by heart, or is it something that's specific to each transformer?
No, so for this, you see, this is no one will know because it is specific, but the range is very limited here. So my own engineering guess, sort of, for an 11 kV transformer, 2.5 MVA, the top liquid temperature will not increase by a few degrees, meaning maybe 2 degrees or 3 degrees. So I would only change, maybe add 5 degrees on that limit, and that should be okay. Because esters anyway, they allow running hotter without degrading the paper. They will not increase the fire risk. But based on other transformers retrofitted for 11 kV transformer, we wouldn't expect 2 degrees increase in top liquid temperature.
Okay, so and just whether it's retrofitted or
yes.
So whether it's retrofitted or new, it'll be the same performance.
Oh yeah, I mean yes, I mean whether retrofilled or a new, if you compare it with a mineral oil to an ester for 11 kV, I expect 2 degrees higher top oil temperature.
And then for the winding temperature, probably pretty
yeah, it can be
higher.
The winding temperature, the copper winding average winding temperature can also be 2 degrees higher or 3 degrees higher.
Yes.
And this all depends on how hot the transformer is operating, the ambient temperature.
Yes.
In winter is different from summer, because in summer you have higher temperature of ambient, but also higher temperature of the transformer. So heat transfer from the transformer to ambient can be more efficient than in winter. Or less efficient, but this is where the assessment is needed.
Okay, I'm going to, I know we're about 20 minutes over already. I'm going to just ask 2 or 3 more questions, and then I'm going to bring the questions to an end. Okay, so are there proposals to bring in some form of marking or identification as a sort of, let's call it standard for the marking of transformers, so that you can quickly identify whether there's ester in or what different type of oils there are? I think the issues around the concerns and risks of cross-contamination.
Oh yeah, so yeah, as I mentioned in the presentation, best practice is you need to identify separately. So separately meaning some utilities paint either green their transformers with esters or blue. I think in South Africa they are painting them blue, or adding a nameplate, another plate near the nameplate of the transformer, where it does indicate clearly that this is retrofilled, say, or filled with an ester. This is the type MIDEL 7131, say. Yes. Otherwise, you will end up in a risk of contamination. Though, I would say, even with contamination, we don't expect failures. The only side effect is reduction in the fire point.
Okay, yes. The next question is an interesting one. Is there consideration about, could you retrofit an old oil-filled circuit breaker with this synthetic ester?
Yeah, this is not a main application for us. We don't do that. And the reason with circuit breakers, they rely really on a mechanical movement. So the breaker need to break and make. Esters have higher viscosity, and so the make and break, during this movement, the parts will face more mechanical resistance, friction from esters. So they will become slower. And when I say slower, it's very, very tiny amount of increase in time. This will cause a sustained arc when they make and break, and so erode the electrodes. As such, esters are not used really in circuit breakers.
Okay. There's a last, I'm going to just bring in, let's just have a look at the last question. I think it was just a question more about the actual process of, it might be a difficult question to answer, but it says here, natural esters, whether the raw material is raw or created through process. What are the typical steps involved in creating raw and synthetic ester? Are there some key activities involved in that process?
For synthetic ester or for natural ester?
It's asking for both, it seems.
Okay, so let me start with the easier one. Well, first, I'm not a chemist, so this is a difficult question for me. But for natural esters, these are extracted from vegetable oils, like canola oil, and then or soybean, and then these basic oils are taken to a factory, refined, dried, filtered, and then additives added at the end of the process. Now, for synthetic ester, as I mentioned, we buy alcohol, certain alcohol, and we buy fatty acids. We mix them together under temperature, and this is where esterification happens. During esterification, water is produced, so we start removing as much water as we can while the ester is being made, and then you go through a filtration process, I think, and then adding some additives, and finally, but these are the basic process of manufacturing. Unfortunately, on my mind, I don't have really the exact steps, but we can direct the one who asked if he can reach me directly. I can supply some information.
No, that's fine. I think we're going to end the questions now. I'd like to hand over to Jay just to do the final close. Jay Kalichuran, can you?
Thanks, Richard. And yeah, that brings us to the end of another learning session. And yes, learnings don't stop there, it continues. So the recording will be made available on the SAIEE YouTube channel, which is called SAIEE TV. It will also be on the SAIEE website. Also, there is an events drop-down menu on the section. Please go to that and you can pick up on the upcoming events as well. And let me also thank our presenter, Dr. Muhammad, for an excellent presentation. It is new, it's a field that we need to move in, and there's lots of advantages. Our appreciation goes to the SAIEE for providing our professionals with a medium to share their knowledge and expertise. Thanks, Minx, for setting it up. Thank you for attending today's session. Thanks very much. Goodbye.